Good morning to everyone. With the advent of science and technology, nowadays buzzwords are data science, big data, machine learning. Mathematics has a major role in these fields. Curve fitting has many real life applications. Firstly, I would like to give an introduction to curve fitting, then about different methods, possible curves, and how to fit these curves using Matlab and few case studies. Let me consider a function f of x equal to 2x plus 5. If x takes the values 1, 2, 4 and 7, so we have the corresponding values are 7, 9, 13 and 19. We know the function here and the values taken by that function, the independent variable, and we have the values of the function at those independent variable values. Let's think about the converse problem. That is, given x comma f of x, you don't know what is f of x. Is it possible to get a function for a value of x not in the table without knowing f explicitly as a function of x? So you have this table in hand, you don't know what is y, and you need to find the value of y corresponding to some x which is not tabulated here. Now the first question is, where does this given function f of x come from? Right? It could be analytical models of phenomena, for example, equations from physics, or it could be creating an equation from observed data, or having a function for the observed data in hand, right? Let me consider an experiment of measuring viscosity of a liquid at different temperatures. Let me repeat. I am trying to conduct an experiment of measuring viscosity of a liquid at different temperature values. I would have noted down V and T for few temperature values. After few months, if I want to know viscosity value for some temperature which was not tabulated, which I had not noted down during the experiment, do I need to redo the experiment, or is there any way? Interpolation is nothing but finding the value of y, the dependent variable, corresponding to some value of the independent variable apart from the table of values, right? So what exactly it does? It connects the dots by a line. So let us think of table of values from x0 to x5, x0, x1, x2, x3, x4 and x5. Corresponding values are y0 to y5. You have 6 values and you can approximate it to a 5th degree polynomial. And you can find the value of y corresponding to some x either within the interval x0, x5 or just outside the interval, right? That is the disadvantage of interpolation. You can have the extrapolation just outside the interval. It could be just before x0 or just after x5. For example, in the previous case, you have these table of values and you can have a f of x value corresponding to say x equal to 0.5 using interpolation. You can find y corresponding to x, say 7.8 or 8.1, not more than that, very much near to 7, right? You cannot expect to have a y value corresponding to say x equal to 50. You cannot make use the process of interpolation. Here, no doubt it is unequally spaced. You may use Lagrange interpolation formula. Suppose we don't know f of x. So in all those cases, you will be approximating it to a polynomial function, right? So it cannot predict the value of y for a value of x which is say very much away from your interval. So if the data is reliable, you can plot it by connecting the dots. That's the direct way of doing it, graphical method. This has interpolation has a limited use as a general function. As I said, you can restrict yourself to a particular interval. It doesn't work very well when you have some built-in random error. So this is an example of piecewise linear interpolation. Each 2 points are connected by a straight line. This is how it looks like. And it doesn't serve as a good approximation. Say your data is very much away from this. You cannot directly join it by a straight line or a polynomial curve, right? So to overcome this, we have curve fitting, which involves capturing of the trend in the data by assigning a single function across the entire range. Yes. So the objective of curve fitting is to theoretically describe the experimental data in hand with a function or an equation and to find the parameters associated with the model. If we use straight line function for the data, which I had mentioned in the case of interpolation, these dots are called the scattered plot. Given observations are plotted here with dots, and this blue line your fitted curve. We have approximated these dots to a straight line. You can observe the values are clustering around a straight line, so straight line is my best fit, right? So in many physical problems, they involve fitting curve to a set of experimental data points, right? So experiments could be the one which I mentioned, viscosity versus temperature, measuring viscosity of a liquid at different temperature values, or it could be measuring voltage V across a capacitor at different time t seconds. It could be in an experiment of friction of bearings, finding the coefficient of friction versus temperature. It could be growth of bacteria in a sample, or voltage and resistance of a carbon filament lamp, or it could be measurement of electric resistance R of a copper bar at different temperatures. It could be measurement of load and deflection in a simply supported beam. This corresponds to every branch of engineering. I suppose I've covered civil, electrical, telecom. Of course, the whole of machine learning data analysis is the field for computer science and information science engineers, chemical engineers, biotechnology engineers, and so on. So curve fitting technique is to find the curve of best fit. We have few methods for fitting the curve. It could be graphical method, method of group averages, method of least squares, method of moments. Among the four, most widely used mathematical way of curve fitting technique is method of least squares. So we are going to learn the method of least squares now, and we are going to fit the curve using Matlab. So it tells you that the sum of the squares of vertical deviations of experimental data from the fitted curve is minimum. What do you mean by that? Let's observe it. And you can use this method to fit both linear and non-linear curves. So you have the values xi, yi given. x1, x2, and so on, xn are the values of independent variable x, and corresponding values of the dependent variable y are y1, y2, and so on, yn. That means you need to fit a curve of the form y equal to f of x. Your y depends on x. So a pair of values x1, y1, and so on, xn, yn are given. Now the method says that the vertical deviations are minimum. Can you just see? So this is square of the vertical deviations. This is your actual data points. Blue points are your actual data points, and this is the fitted curve. I have taken an example of a straight line y equal to ax plus b. For this data which is clustering around a straight line, we have y1 here, the dot, actual point is y1, and y1 hat is here. So y1 minus y1 hat whole square plus y2 minus y2 hat whole square. This is your actual point, and this is the fitted curve, right? Fitted point on the fitted curve. Similarly, y3 and so on, yn. It tells you that sum summation yi minus yi hat whole square should be minimized. Our minimum, our aim is to minimize this. So generally it is not possible to find the actual curve. We go for an approximate curve y equal to f of x, and that is referred to as curve of best fit. You may not be able to find the exact function, but we are going to find an approximate function, and the process is called curve fitting. And here the method used is method of least squares. So we have this, I have already explained, and let's recall what all possible curves are there. It could be a straight line of the form y equal to a plus bx. It could be y equal to a by x plus b. It could be y equal to a e power bx, or y equal to a x power b, or y equal to a b power x, or it could be a second degree curve, parabola y equal to a plus bx plus cx square. So let us just quickly recall fitting a straight line. You have the error estimate given by yi minus yi hat, right? So you are trying to, this y is your actual data. You are trying to approximate it to a plus bx, right? So this is your yi hat. And by the principle of least squares, you have y minus yi hat whole square to be minimum, correct? So parameters which make this minimum are a and b. So let's recall the maxima minima, differential calculus. How will you find maxima minima? First derivative should be 0, right? Here two parameters are there, namely a and b. So you have to take partial derivatives. Dou e by dou a is 0. Dou e by dou b is 0. You're going to differentiate this partially with respect to a, equate it to 0, and then partially with respect to b and equate it to 0. So 2 times. So you had yi minus yi hat whole square. So 2 times that into derivative of minus a. So this derivation would have been done in the class, and rearranging, taking summation throughout. Can you just tell me what is summation a? You are adding a n times, right? You have n values, xi, yi, I varying from 1 to n. First equation is summation y equal to n times a plus b summation x. Similarly, considering second derivative, I mean dou e by dou b, derivative with respect to b, and simplifying, derivative of minus b is bx is minus x. Rearranging, you have the equation, and these two are called the normal equations to fit a straight line, right? Let's recall the working rule quickly. Given xi, yi, that means table of values x1, x2 and so on xn, corresponding y1, y2 and so on yn. First thing we do is we write the normal equations. Our aim is to find a and b. Now my question is, do we know x? Do we know summation x here? Our aim is to find a and b, which are unknowns here, right? A and b are the unknowns. Do we know summation x? So x table will, x column, you can tabulate the values column wise. So x column will be given, you just add them and you get a summation x. Similarly, xy is given, so you have y and summation y. And what else you need? These two are known from the given table. Next you need is summation x square. So you add one more column there, which is x square, right? You find out summation x square. You find square of each values and do that. And the last column you need is xy. You can use calculator. Go to alpha mode. Just define alpha x square. You have the letters written in red color. So alpha x square, alpha colon, alpha x, alpha y. Quickly get horizontal values for each of the x and y values, right? So next step is substitute these summation values in the normal equations. Use calculator, go to equation mode. It will ask number of unknowns. You have two unknowns here. Just substitute the coefficients and get A and B. And substitute back in the required equation of best fit, y equal to a plus bx. That will give you curve of best fit, right? That is which is straight line in this case. Now I'll come to the actual thing, that's using Matlab. I had given the method of least squares for straight line. Hope you know the same thing will be extended in case of parabola. You will have one more parameter c. So you are going to differentiate partially with respect to c. Dou e by dou c, equate it to 0, get one more equation. So you have three equations, three unknowns, you solve it, you get ABC, substitute back in y equal to a plus bx plus cx square. That's the case of parabola. For the remaining curves which I had mentioned, a e power bx, a x power b and a b power x. Can you just tell me what happens in those cases? You try to reduce them to the form of a straight line and then you use the normal equations for a straight line and get back in terms of the original unknowns there. In terms of small a, small b, you just use log a as capital A and proceed, log y as capital Y and proceed, and finally you write it back in terms of the original variables. I'm keeping in mind that the topic is over and I'm just recalling what all you have studied. Now we have come to the important point where you need to learn how we are going to code it using Matlab. So let me just quickly tell you the syntax and description. It is just fit object. You can give any name here, and actual syntax is fit x comma y, and you need to specify the fit type. What type of curve you need, whether it is a linear curve, that is straight line, or it's a second degree polynomial, which is a parabola, or it is an exponential curve in the form a e power bx, or it's a power curve in the form, general form ax power b. So all these are specified by fit type. So this is one line syntax you are going to use in Matlab to find the curve of best fit, and you need to know what all fit types are available. I'll just explain that part. You can have a linear model by inserting poly 1 here. In place of fit type, you have to give in single quotes as a string input poly 1. P should be capital. Matlab is case sensitive. You need to give this as P, and remember your function fit. All letters are in lowercase. You have lowercase letters here. It is case sensitive, and you just have to remember fit type for straight line is poly 1. One advantage with Matlab is I'll just open the window. I'll explain. You have an help option wherein you can explore the codes for corresponding topics. Quadratic model, in place of fit type, you are going to give poly 2. What is this xy? X is your given x values, y is your y values. That will be beginning input as row vectors. I'll explain that with an example. So for quadratic model, you have poly 2, which will give you the answer p1x square plus p2 plus p3. It will give you the values of p1, p2 and p3, which are the required values. And then you have the general model exp of 1, which gives you a curve of the form a e power bx. The last one, you have power curve, which is specified with power 1. Is that clear? I'll open Matlab window and explain with example. You will understand it in a better way. For time being, you can just take a pic of this slide so that you can just try with Matlab code. Done. So let's start with an application example I have taken here is latent heat of vaporization of steam are for different temperatures. So temperature values are tabulated as 40, 50, 60, 70, 80, 90, 100 and 110 and corresponding R values are specified. You need to fit a relation of the form R equal to A plus BT. That means you have to make a straight line fit here. So, okay, I'll just give you table of values. Yes, summation T is 600, good. So these are the summation values which were required to solve the normal equations, right? Our aim is to find A and B. N equal to 8 here. So I'll just give you values of A and B. A is 1091, B is, just remember the value, we'll just see using Matlab. Right? So let's move on to Matlab code for this. So remember x equal to, if you write the values in square bracket, forget about this prime for a moment. It gives you a row vector having these values. You can separate each value by space or spacing, or you can put a comma in between to separate each of the values. Forget about prime. Values written in square brackets will return a row vector, right? Correspondingly, the values of y are given like this. Either you can separate them by spacing or you can put a comma in between. Now why prime is required here is you want to have them as a column vector. As you have seen in the previous slide, we need to, whatever the table given, we write it vertically column wise and compute summation values, right? Same way it is done here in Matlab inbuilt also. You just have to input them as column vectors. And then as I mentioned, I have given f equal to fit x comma y and the fit type. I had mentioned different types, right? I have taken poly one because I am fitting a straight line here, correct? And this was just to obtain the values of A and B. I want to compare the actual data points and the fitted curve. So I will plot of f comma x comma y will give me a plot wherein I can see the data points as well as the best fit curve, so that I can compare the two, whether my points are clustering around the same curve or not. So I have this as the output. Okay, this is the graph you are going to get. Got the output? It has given A and B values. Can you just see? So your Ax plus B form means A is minus 0.5443, X plus 1091. And this is the curve. Okay. Yeah. Now these blue dots are the observations data, right? And this red line is your fitted curve where we have fit a straight line here. You can just see almost all points are, curve is passing through almost all points except only one. So method of least squares will give you the best fit. If you keep your cursor, you can just see, you can get back the table of values also. Okay, it's just very small deviation here, and this is the best fit we have got, straight line fit. Forget about red line. If you observe just the dots, you can easily make out those dots are clustering around a straight line, and you can decide. Here in the class, teacher will give you some problem, fit a straight line, fit a parabola, fit a exponential curve. You may be wondering why we have to do that particular curve. The concept of data analysis is they just take thousands of data, they make a scatter plot, they draw it like these dots, and they see the trend and they decide whether they have to fit a straight line, fit a parabola. In class, we can only take finite data and make you understand how exactly curve fitting works. So learning the theory behind that is very important. You can do debugging only when you know the concept, right? If you go wrong somewhere and you want to correct yourself, you should know the logic or theory behind that you are going to learn in the class, right? So now I want to take up next example. So for that code, I will just give a section break. You have an option section break here, so that I can type the next code in the, after the section break, I need not have to run the first code every time. It will avoid running previous code. You are running only that particular section. So let me take another example. You have results of measurement of electric resistance R of a copper bar at various temperatures T, and you need to fit a relation of the form A plus BT. So as you already know, these are the normal equations. Let's quickly have this table. So these last values are the summation values. You substitute back these summation values here, solve for A and B, and finally these are the A and B values. Let's try to have Matlab code for this. I'm taking up so that you will learn the software also simultaneously. This you would have learned in the class. Again, it's a straight line fit for a different data. Procedure remains same. So you have X, you are giving these values and give it with a prime, which will make it a column vector. Similarly, Y, another column vector. And the syntax for curve fitting is fit X comma Y comma, since it's a straight line again, polygon. And you need to plot f of X comma Y. So these are the answers. We'll just see in the Matlab window. Can you just see? Earlier it was decreasing curve. Now it's an increasing curve. And here you have the values of, hope we have got back the same values. We'll just cross verify. Yes. Yes. 70.05, 0.2923 by manual calculation. And here using the software, we have got the same values, right? P1 and P2. It fits the curve of the form P1x plus P2. And this is the graph. I'll show you in a separate window so that we can analyze. Again, this was a small data. We could have these dots here. Forget about red line for a moment. Observe blue dots. You can make out we have to fit a straight line for the data. So this is your fitted curve. Red line is your fitted curve, which will follow the method of least squares. Vertical deviation of each point, fitted point from the actual point, that should be minimum. It follows the principle of method of least squares, and this is done. At the back end, what works is your method of least squares. Now to fit a parabola, I've taken an example of results of measurements of train resistances, and V is the velocity in mile per hour, R is the resistance in pound per ton. So you have V versus R versus V. So you need to fit a curve of the form R equal to A plus BV plus CV square. That is, our aim is to find the values of ABC. So can you just recall the normal equations? You have three equations, right? These are the normal equations to fit a parabola. You need three equations because three unknowns are there. And then these are the summation values I've directly given because there is no space here to put the table. And these are my ABC values, right? Now let's see how we do it using Matlab. So you have poly 2 here. Input for X and Y remains same. You have to give them as column vectors. Just your fit type will change now to poly 2. So it gives you, in this case, p1 x square plus p2 x plus p3. So these are the coefficients p1, p2, p3. And this is your fitted curve. You can just see blue dots how nicely coincided by the fitted curve. We'll just try doing this on Matlab. It's perfectly matching. And let's observe the graph in new window. Yes, blue dots are your data points and red line is your fitted curve, which is a parabola, second degree polynomial, and see how nicely they are coinciding, right? So the data, best suited curve for the data was a parabola in this case. Let me take an interesting example. So following table gives you number of days X and percentage of people affected by spread of virus Y. It could be the current situation, spread of coronavirus, but the data appears like it was during the first wave, right? Not now. Maybe during the first wave in a small town. First day it was 5 people affected, second day it was 10, fourth day it was around 30 people. I've taken a small data just to make you understand. It's an exponential increase from 10, suddenly it has increased to 30. That itself tells you that it's an exponential growth, right? So let's see. You have a curve. Now what you do, you just take log on both sides to reduce it to a straight line form and use the notation capital Y for log Y and capital A for log A. Corresponding normal equations are given by this. And these are the summation values. Now you have summation X. You will have one more column Y change to log Y. You have to take log to base E would be better here because you have E. When you take log on both sides, you have log A plus bx log E to base E, which becomes 1 here, right? So better take log to base E and then find the summation values. So finally, I have capital A and B, which I have to change to small a, and then B is here. So these are the values. Now let's see. So this is the curve which we are going to fit. Can you just see the blue dots here? 1, 2, 3 points were there and it's almost passing through all the points, right? So we have best fit to be an exponential fit for the data and it happens to be possible here. This is the best fit for the exponential growth we have observed here. So let's see few case studies. It could be to develop numerical calibration procedures for a river water quality model. I'm trying to take a few case studies which involve large data. So it could be climate change for high leverage points and outliers of wind speed prediction for test data collected from a wind farm. It could be agricultural or engineers or biologists who often need to develop and use functions in order to explain observed events, perform predictions under different scenario, find relevant characteristics of data such as growth rates and so on. It could be in modeling objects from monocular image sequences, or it could be for fitting results from reaction calorimetry. Even our students had taken data of air pollution, what all chemicals are present before lockdown, and they have studied during lockdown, and they are doing a project on that where they try to fit a curve. They see whether the pollution has decreased exponentially or it has decreased in a straight line manner and so on. Thank you.